Hello everyone, hello dear students. Today we are going to discuss a new topic, a new chapter, that is crystallography, or simply known as solid state. So before starting with this solid state or crystallography, let's define what is solid, what are different types of solids, and the basic difference or basic properties between different types of solids. So look at this, we have three physical states of matter: solid, liquid and gas. Now the basic difference between these three physical states of matter is the binding force between the components. If the binding force between the components are very strong, meaning thereby when the components are very close to each other, the attractive force between the components of the matter will be very strong. If the components are very close and attractive force is very strong, then that particular state of substance matter is what we call a solid state. If the particle distance between the components are large, as the distance between the components is increased, the attractive force between the components will be least, and that particular state is what we call as gaseous state. In between these two extreme forms, when the distance between the particles is very large or the distance between the particle is very small, in between these two we have a particular state in which the attractive force between the components is in between the solid and the gas. That particular state is what we call as the liquid state. In liquid state, the attractive force between the components is less than that of solid but greater than that of gases. So basically we have a solid. The distance between the components is very small and the attractive force is very high, resulting in a physical state known as solid. So we have a solid. Now these solid can be classified into two. One is known as crystals, the other known as crystalline solid, or the other one is known as amorphous solid. So we have two types of solid: crystalline solid and amorphous solid. Now let's define what is this crystalline solid and amorphous solid. First of all, when you say crystalline solid, all crystalline solids have a regular repetitive arrangement of the component or the constituent throughout the crystal. That means if you take this to be molecular crystals, then the molecules are arranged in a regular repetitive arrangement throughout the crystal. Or if we consider the constant to be atoms, again these atoms are arranged regularly throughout the crystal. Or if these can be ions, so the cations and anions are arranged regularly throughout the crystal. That means there is regularity in the arrangement of the constituents of a solid. That type of solid is what we call as crystalline solid. If the regularity of the arrangement of the constituent is irregular, then we say this is amorphous solid. So basically, in a crystalline solid, there is a regularity in the arrangement of the constituent of a substance, solid, whereas in case of amorphous, no regular arrangement. So the first one is a regular and repetitive arrangement of constituent particles throughout the crystal. So this arrangement is throughout the crystals. So this regularity and the repetitive arrangement is what we call as long range order. That means this order in arrangement of the constituent particles is extended throughout the crystal. So arrangement is long range order. Whereas in case of amorphous solid, there is no regularity in the arrangement of the constituent particles, but these regularities only up to a very short distance or a limited range. Beyond this, there is no regularity. So simply we say, in case of amorphous solids, there is no regularity and arrangement, and if at all there is a regularity, that regularity is only up to certain limited distance. So we say these are short range order. No regular arrangement. But we can have regularity only up to certain extent. So we say this is short range order. Short range order. So first point of difference is there is a regularity in the arrangement of the constituent particles, which is known as long range amorphous. The regularity is not observed, but sometimes the regularity only up to certain limited extents, a very short distance is observed. So we say this is short range order. Now, due to this short range order, there may be some regularity in the substance for a short distance. Beyond this distance, again the regularity is not observed, and this short range order causes crystallinity. Some of the molecules, components may undergo crystallization for a very short distance. Beyond this, the constituent does not crystallize. These type of thing is observed in glass objects of ancient civilization. These glass objects of ancient civilization is found to be milky in appearance due to crystallization. Means when this glass-like substance over a very long time, that is ancient civilization, there may be some crystallinity of the constituent particles. Beyond this, the crystallinity again disappears. Due to this short range crystallinity, these glass-like objects appears milky in appearance. So this is one of the example of short range order. Second point of difference between this crystalline compound and amorphous compound, as we all know, crystalline compounds have sharp melting point, where amorphous compounds does not have sharp melting point. Does not have sharp melting point. So this is one difference between these two. Third point of difference is crystalline compounds are known as anisotropic Whereas amorphous compounds are known as isotropic. So we have very new term here, anisotropic and isotropic. So let me explain what is the meaning of anisotropic and isotropic. Now in crystalline compounds, we are saying there is a regularity and the repetitive arrangement of the constituent particles throughout the crystals. So due to this regularity, the arrangement of constituent particles in different directions will have a different arrangement. So there are some physical properties like electrical conductivity, electrical resistivity, thermal expansion, refractive indices, etc. When these physical properties are measured in a crystalline compound, the same physical property shows different values in different direction. If the direction of observation of measurement of the physical properties is changed, then for the same physical property, different values are observed. So this phenomenon is known as anisotropic. So crystalline compounds shows different values of the same physical property when the direction of measurement is changed, or the direction of observation is changed, or the angle of observation is changed. These properties due to different arrangement of the constituent particles in different direction. That is what we call as anisotropic. Different values of same physical properties in different direction. So same physical property shows different values in different direction. This is due to different arrangement of constituent particles in different direction. So the physical properties may be a refractive index, electrical conductivity or resistance, or thermal expansion, etc. So these physical properties when measured in different directions shows different values, though the crystalline is same. And I'm again repeating why these are showing different values of the same physical property in different direction. The reason is because of different arrangement of constituent particles in different direction. Though we have a regular repetitive arrangement, but the arrangement are different in different directions. So we are having different values of some physical property, that is anisotropic. Whereas in case of amorphous compound, there is no regularity, or the regularity is up to very certain limited extent. Since there is no regularity in the arrangement of the constituent particles in amorphous solid, the same physical property shows same values when observed in different directions. That property is known as isotropic. What we are observing is the average value of the same physical property in different direction. That is known as isotropic. Same value of physical properties when measured in different directions. So this is one of the most important criteria or difference between these two crystalline compounds and amorphous compounds. So again I am repeating, anisotropic means the same physical property when measured in different directions shows different values due to difference in arrangement of the constituent particles in different directions. That is anisotropic. When the same physical property is measured in different direction, the values are found to be same. This is what we call as isotropic. And why amorphous compounds are isotropic? Because these amorphous substance does not have regularity in the arrangement of the constituent particles. So this shows same physical values, same values of the physical properties when measured in different direction. Crystalline compounds, these are known as Q solid, Q solids. Amorphous compounds are known as pseudo solid, or they are also known as super cooled liquid. So we are using a term amorphous substance or solids are pseudo solids or they are super cooled liquids. Why they are called super cooled liquids? Liquids are fluid, they have fluidity, tendency to move. So amorphous substances are also known as pseudo solids or super cooled liquids. Why they are called liquids? Because they show fluidity similar to that of liquids, tendency to move. Now, one of the very important example which shows super cooled liquid nature of amorphous substance. We know glass. Glass is an amorphous compound. Now, these glass shows tendency to move, fluid in nature. Now, if you look at the glass used in window panes and the doors of old buildings, if you observe the glass used in window panes and the doors of old buildings, the glass appears to be slightly thicker at the bottom than at the top. We are having a glass which is used in window panes or doors of old buildings. These glass appears to be, or if you observe the glass, these are slightly thicker at the bottom than at the top. This is due to the very slow movement of glass from top to bottom. So if glass particles are moving from top to bottom, the thickness of this glass at the top appears to be less, and since glass is moving towards the bottom, so bottom position is slightly thicker. So these clearly shows if these amorphous compounds or amorphous solids are not true solid but super cooled liquids. So we have this. The rest we have number of difference like these crystalline compounds or crystalline solid when they are cut by a sharp edge weapon, they give a clear edge. But in case of amorphous compound or amorphous solid, when they are cut by a sharp edge knife, they does not give clear edge. So these are some of the difference between these crystalline compounds and amorphous compounds. So basically we have this crystalline and amorphous. Now the chapter says this is crystallography. So basically we will be dealing with the crystalline compounds. So after having this basic difference between crystalline compounds and the amorphous compounds, let's go to the crystalline compounds. That is classification of crystalline compound. Classification of crystalline compounds. These crystalline compounds are basically of different types. Molecular crystalline compounds, metallic crystalline solid, covalent or network crystalline solid, and ionic crystalline solid. So crystalline solids are basically classified into four different types. We have molecular, metallic, covalent or network, and ionic. Now let's see the difference between these different forms of crystalline solids. Now these molecular crystalline solids, the basic constituents are molecules. That means the constituent unit of molecular crystalline solids are molecules. Since we are having a molecules, the attractive force between the molecules will be either van der Waals force or London dispersion force or dipole-dipole interaction or hydrogen bonded system. Based on this, these molecular crystal is classified into different. First category of molecular crystals is non-polar molecular crystals. Now look at this, we are saying non-polar. That means the electronegativity difference between the components of the molecules will be zero. If the electronegativity difference is zero, then we say the molecule is a non-polar molecule. So in case of non-polar molecules, the attractive force between the components will be weak van der Waals force, which is known as London dispersion force. So here electronegativity difference is zero. We have this example: helium, neon, you can have a look at this, Cl2, etc. So these are molecules in which the electronegativity difference between the components is zero, and these molecules are known as non-polar molecule. If they can be crystallized, then these comes under molecular non-polar crystalline solid. Now these non-polar crystalline compounds, the attractive force is London dispersion force, which is very weak in nature. Due to this London dispersion force, these non-polar molecular solids are generally soft, having low melting point. Now, second type of molecular crystal is polar compound, polar molecule. Now, when we are using the term polar, the components of the molecule will have difference in electronegativity. That means there is a polarity, positive pole and negative pole developed in the molecule. Because of this development of dipoles, molecule is said to be polar molecule. And in case of this polar molecule, due to the development of this dipole, the attractive force between various molecules of the crystal will be dipole-dipole interaction. So this dipole-dipole interaction is stronger than that of London dispersion force, but this is also weak force, which is known as van der Waals force. Because of this, again, these are again soft and having low melting point. So in case of this, electronegativity difference is not equals to 0 and we have a dipole. So example of this is we have HCl, we have H2O, we have ammonia, etc. Now in this the attractive force is van der Waals force. That is dipole attractive force. The third category of molecular crystalline solid, that is hydrogen bonded crystalline molecular solids. Now as the word suggests, hydrogen bonded, that means the molecule must have hydrogen which is covalently bonded to a strong electronegative atoms like nitrogen, fluorine or oxygen, and these hydrogen which is covalently bonded to electronegative atom is involved in a specific bond which is known as hydrogen bond, and the attractive force between the molecules of these crystal is through hydrogen bond. So these molecules are known as hydrogen bonded molecular crystalline solids. So in case of this, we have examples like H2O, NH3, HF, etc. So hydrogen is attached to electronegative atom, oxygen, nitrogen or fluorine. So these hydrogen get involved in hydrogen bond. So the attractive force in this category of solid is hydrogen bond. So these molecular crystals of this non-polar, polar hydrogen bonded, the attractive force between the molecule is van der Waals force. Strength of van der Waals force, that is strongest in case of hydrogen bond, weakest in case of London dispersion force. Since the attractive force between the components is weak force, so these compounds or these solids are generally soft, either they exist in soft solid or liquid or gaseous form, and they have low melting point. Coming to second category, that is metallic crystals. Now in these metallic crystals, the constituent of metallic crystal is metal ions surrounded by an ocean or sea of electrons, or simply we say is the atoms, or we say these are metal atoms. So in metallic crystals, the constituent particles are metal atoms. Now the structure of metal is defined by a model which is known as electron sheet model. So it's a very important model which is used to describe the structure of crystalline structure of metals or metallic bonding. So let me give you a brief what is electron sheet model. Now the crystalline metal or metal crystals are considered to be, or the metal crystal is composed of the metal ions which is known as kernels, positively charged metal ions, also known as kernels. These positively charged metal ions known as kernels are surrounded by an ocean or sea of negatively charged electrons. So we have a metal ion, positively charged metal ion, which is known as kernel. This is surrounded by an atmosphere of negatively charged free electrons. Now these metals having low ionization energy is easily ionized to form metal ion, that is kernel, and electrons are easily removed. So these kernels or metal ions are surrounded by an free of electrons, and these electrons are completely mobile and they can move throughout the crystal, and these mobile electrons act as a cementing force or link between the positively charged metal ions. So this is responsible for the metallic bond. So in case of metal, we have a metal ion surrounded by an atmosphere of electrons. Electrons are completely mobile. They can easily move throughout the crystal, and these electrons are acting as a cementing link between positively charged metal ions. And this attractive force between the metals in metal crystal is what we call as metallic bond. So we have positively charged kernels. These positively charged kernels are what we call as metal ions, and in between these we have electrons. So these negatively charged electrons are coming from ionization of metals with low ionization energy, and these electrons act as a link or cementing force between positively charged kernels. So this is metal ion. This is known as kernel. This is free electron. So these electrons are completely mobile, moving throughout the crystal, and these electrons is acting as a link between these positively charged metal ions. So this is what it was electron sheet model. So here we have a metal ion known as kernel surrounded by a layer of electrons completely mobile. Now since metal crystal contains a large number of mobile electrons, because of these mobile electrons, these metals are very good conductors, and conduction is because of the movement of these mobile ions electrons throughout the crystal. Again we are saying that these metals are lustrous shining property. Again the shining property or the lustrous nature of metal is again because of these mobile electrons. When we supply energy, electrons absorb energy, and these electrons oscillate about their mean position. When these electrons oscillate around this mean position, energy is released in all possible directions, which appears as lustrous or shining property. Again, we are saying that metals are highly malleable and ductile. Ductile means this can be into a thin wire-like forms, and malleability means this can be spread into a thin sheets. So the malleability and ductility of the metals is again because of these mobile electrons. Now when we hammer these metals, these layers slip each other without disturbing the arrangement of kernels and electrons. Due to this sliding property, these metals again shows malleability and ductility. So this is metallic crystals. In these metallic crystals, the constituents are atoms, and these are explained by electron sheet model. Now coming to third category of crystalline solids, we have a covalent or network. Now in this covalent or network, again the constituent particles are atoms, and these atoms are bonded throughout the crystals to a covalent bond which is extended in three dimensions. So we have an atoms are bonded through covalent bond throughout the crystal in a three-dimensional network, resulting into a network molecule. So this is three-dimensional covalent network. Now, because of this three-dimensional covalent network, these covalent or network compounds are generally hard, having high melting point. The best example is we can have diamond, we can have silicon carbide, we can have silica, etc. We can also have a graphite. So these are covalent of network. Except this graphite, these are very hard substance. Due to this three-dimensional covalent network, graphite is soft because the covalent network is two-dimensional here. In between these two layers, again there is a weak van der Waals force. Now, since the atoms or molecules are bonded through a covalent network, three-dimensional, these are giving very hard substance. In case of ionic crystals, the constituent particles are ions, that is cations and anions. Now, since we have charged particle which is cations positively charged and anion negatively charged, so we have ions which are oppositely charged. Due to this, the attractive force between the constituent particles are very strong electrostatic or Coulombic force. This strong or attractive force results in these ionic crystals to be very hard substance having a high melting and boiling point. And these ionic crystals are non-electrolytes in solid, but they show electrolytic property in molten state or in solution. In molten state, when these solids are heated, they come close to give you cation and anion, and these cation and anion can conduct electricity. Or when these are dissolved in water, these being a polar compound, these are soluble in polar solvents. So when these are dissolved in water, this ionize to give you free metal and free anion, and again this can conduct electrical conductivity. So ionic compounds are hard because the attractive force between the constituent cations and anions are very strong electrostatic force. These ions are not free to move, so at solid state conductivity is zero. But at melt form or in aqueous solution, due to the presence of free cation and free anion, there shows conductivity. So these are different classification of crystalline solid and their basic properties. Now, once we have this crystalline, so again we will discuss the basic properties of this crystalline solid or crystals. So we are coming to the crystals. Now, in crystals, we have to study the basic repetitive unit. Once we identify the basic repetitive unit, then we can easily construct the crystal. So the basic unit or properties to identify this basic unit. Once we identify the basic unit, we can arrange in all possible directions, and this will give you the regular crystal. And the repetitive unit which on arrangement throughout the solid gives you the crystal. That basic unit is known as lattice. So we have a term lattice. So this is regular, repetitive, arrangement of points such that at any point the surrounding is exactly same at every point. If we take the surrounding of a particular point, at a particular point, the surrounding will be same with another point. So this is what we call as lattice, and every point of lattice is known as lattice point. So look at this, we have used a term regular repetitive arrangement of points such that the surrounding or the environment of any point is similar or same with every other point in the crystal. That is what we call as lattice. And every point of lattice is known as lattice point. It is known as lattice point. Now these lattice points should have some features. There are some features or properties of this lattice point. Now these lattice points are always joined by straight line. Now we have a lattice in which points are arranged in such a way the point at the surrounding of one point is exactly similar to the surrounding of any other point, and each point is known as lattice point. So in a lattice we have a number of points, and between any two points the line joining any two points should be straight line. So any two lattice point cannot be joined by a curved line or a zigzag line. So one of the very important feature of this lattice is we have a lattice point, and each lattice point is joined through a straight line. Now these points, when extended throughout the crystals, gives rise to the crystal. So we have this lattice, we have this lattice point, and all lattice points should be joined by a straight line. Now this lattice can be identified in two-dimensional form or three-dimensional. So let's go to two-dimensional lattice. Two-dimensional lattice. Now we have to look at it simply. Square lattice. Let's suppose this is A, this is B, then A is equals to B, and this angle is equals to be 90 degree. So we have a lattice point here, lattice point, lattice point. So this is a lattice. Second is rectangular, rectangular lattice. This is A, this is B. A is not equals to B, but angle is 90 degree. We can have hexagonal, these are a lattice point. This is A, this is B, so A is equals to B, regular hexagon. Fourth, we can have parallelogram. A, B. So we have A equal to B, or we don't have A equals to B, but the angle is not equals to 90 degree. We can have rhombic. So these are 5 possible two-dimensional lattice in which the points can be arranged in different forms. So A is equals to B, angle is not again equals to 90 degrees, something between 90 and 30 degrees. So these are two-dimensional lattice in which the points can be arranged in different form. Now coming to three-dimensional lattice, that means we are going to discuss the arrangement of these points in three dimensions. Now to define this lattice, we define the arrangement of points and the basic structural three-dimensional or the smallest three-dimensional arrangement of points in any crystal that is known as unit cell. So this is the smallest three-dimensional arrangement of points. So we have the smallest or the basic structural arrangement of points in three dimensions is known as unit cell. So once we identify this unit cell, we can place these unit cells side by side throughout the length and breadth of the substance, and we can construct the crystal. So unit cell is not the crystal but combination of unit cell, arrangement of unit cell in all possible directions. There is a regular repetitive arrangement of unit cell. That regular repetitive arrangement of unit cell gives rise to crystal. So to identify the crystal, we have to identify the smallest three-dimensional arrangement of points, which is known as unit cell. So we have to identify the unit cell, then place this unit cell in all possible directions, and this gives rise to the crystal. So the property of crystal is basically the property of this unit cell. So unit cell in a cubic unit cell. So basically we have this cubic unit cell. So to define this cubic unit cell, we have a cube like so we have a cube like structure. These are the edges. Let this be A, this edge distance is B, this edge distance is C. So to define this cubic unit cell, we should have edge length A, B and C. Along with this, we should also have this angle between the edges. Let this be alpha, this is beta and this is gamma. So to define this cubic unit cell, we should have the knowledge of edge length A, B and C and angle between the edges, that is alpha, beta and gamma. Now this combination of different values of A, B, C and alpha, beta, gamma gives rise to 7 crystal systems. So we have to see the possible combination of A, B, C, alpha, beta, gamma. So these gives rise to 7 crystal systems. So I am giving the crystal systems and their possible values of A, B, C and alpha, beta, gamma. So first one is cubic, second orthorhombic, third one tetragonal, fourth one monoclinic, fifth one triclinic, sixth one hexagonal unit cell, seventh one rhombohedral. So these are the 7 possible crystal systems. Now let's define this alpha, beta, gamma and ABC. Now in a cubic unit cell, the A's length A is equals to B equals to C. Cubic unit cell, A's length A equals to B equals to C, and angle between the A's, so alpha equals to beta equals to gamma equals to 90 degree. So if we have this combination, this is known as simply cubic crystal. Orthorhombic, A is not equals to B, not equals to C. The A's lengths are different, but angle between the edges are identical, which is equals to 90 degree. If we have this combination, that is orthorhombic. Tetragonal, we have this two A's lengths are identical, but the third one is not same. And the angle between the edges are all 90 degree. So we have this tetragonal unit cell. Then we have monoclinic, A not equals to B not equals to C. So in case of monoclinic, the A's length A, B, C are different. Then alpha equals to beta, this is equals to 90 degree but not equals to gamma. So two of the angles are 90 degree but the third angle is not 90 degree. Then we have this monoclinic form. Triclinic, edges are different and the angles are also different. Then we have this triclinic form. Then we have hexagonal. In case of hexagonal, two edges are same but not the third one. And two angles alpha, beta equals to 90 degree but the third angle gamma that is equals to 120 degree. Then we have hexagonal. Rhombohedral, A equals to B equals to C. The angle between the edges are same but not equals to 90 degree. These are the 7 possible crystal systems. So we have this, so you should know the combination of these things, A's length as well as the angle between the A's. Now though we have 7 crystal systems, in these 7 crystal systems, there are again 4 possible arrangement of lattice point. So look at this. We have total 7 crystal systems, and each crystal system can have 4 possible arrangement of unit cell. So each of these crystal systems can have 4 possible arrangement of lattice points in unit cell. So there 4 possible arrangement are simple or primitive unit cell, body center unit cell, face center unit cell, and center unit cell. So we have these 4 possible arrangement of points. So look at this. For 7 crystal system, each crystal system there are 4 possible arrangement of lattice point. So therefore total lattice system, total possible lattice system is equal to 7 into 4, 28. So theoretically there are 28 possible lattice systems. These are 20. So we have 7 crystal systems. Each crystal system have 4 possible arrangement of points. So total possible is 28. So 28 possible, theoretically possible lattice systems are there. So out of these 28 possible, only 14 exist in nature. So there are possibility of 28, but only 14 exist in nature. These 14 naturally existing lattice systems, these are known as 14 Bravais lattice. So Bravais lattice are the 14 naturally existing lattice systems, which is known as Bravais in honor of scientists who discovered it, that is Bravais. So theoretically possible lattice system is 28. Out of this 28, only 50%, that is 14 exist in nature, which are known as Bravais lattice. So there are total 14 Bravais lattice. So why look at this? Total crystal system possible 7. Each crystal system can have simple or primitive body or phase center of n center. So these are Bravais lattice. These three, body center, phase center, n center, these are known as centered unit cell. So let me give you the different arrangement of lattice points. In simple or primitive, only the corners of cube lattice point is only the corners of cube. If the constituent occupies only the corner of cube, then we say this is simple or primitive unit cell. The remaining body center, face center. So in case of body center, we have lattice point that is occupying corners of cube. Along with this corner, a lattice point is also found exactly at the center of cube. So we have lattice point occupying corners as well as center of body. So we say this is body center cubic unit cell. Then we have face center. In case of face center, lattice point is again corners of cube. Along with these corners of cube, there is also lattice point at the center of each face. We have center of this face, so we have a lattice point here. Center of top face, we have a lattice point. Center of bottom face, we have a lattice point. Center of left face, again we have a lattice point. Center of front face, again we have a lattice point. And the center of rear face, again we have a lattice point. So along with the corners, lattice point also occupies the centers of face, which is this is face center cubic unit cell. Now in case of n center, as is when we have lattice points occupying corners of cube. Along with these lattice points at the corners of cube, any two opposite face has got face center. It can be the front face or rear face, or it can be left or right face, or it can top or bottom. So along with these corners, any two opposite face has got face center. This is n center cubic. So these are four possible arrangement of points in unit cell. Simplest, we have body center, face center, and center. So out of this, simple body center, face center, and end center. Only the first three is mentioned in our syllabus, so but we are going to discuss these three. We are going to ignore this end center for the time being. So this is unit cell, and turn off like this function unit cell. Now once we define this unit cell, now let's define effective number of spheres or atoms per unit cell. Effective number of spheres or atoms per unit cell, which is also known as rank. So we have to define the effective number of spheres present per unit cell, that is rank. Now there is a simple formula to define this rank. So rank R, rank is defined as Z. So we have Z, this is NC by 8, NF by 2, NE by 4 plus ND by 1. By this NC, number of atoms or spheres occupying corners of cube, and FC for corner, number of atoms occupying face center of cube, F for face center. E, number of atoms occupying edge center. This is edge if there is a possibility of finding atoms at the edge. And B, number of atoms occupying body center. So we have number of atoms occupying corner, face, edge center, and body center. But number of atoms occupying corner is divided by 8. That means each corner atom is equally shared by 8 unit cell. Now since each corner atom is equally shared by 8 unit cells, so the contribution of this corner is 1/8. And 8 by 2, so we have a face center. This face can be shared only with 2 unit cells. So we have a unit cell, above this we can place another unit cell. So this face is common to 2 unit cells. So the effective contribution of this face center atom is half. Edge center, so we have an edge. This edge is common to 4 unit cells. So we have unit cell, place 1 unit cell, 2. Above this we can also place 2 unit cells. So each edge is a combined property of 4 unit cell. So effective contribution is 4. And we have a body center. In a cube only one center, and this body center is shared with only 1 unit cell. So this is divided by 1. So this is the contribution. So once we know the position of atoms or spheres, we can easily define the rank, that is effective numbers of atoms per unit cell. So therefore look at this. In case of this simple or primitive unit cell, we have only corners. So how many corners? 1, 2, 3, 4, 8 corners. Number of corner atoms is 8, and contribution of each corner atom is 1/8. There is no face center atom, there is no end center atom, there is no body center atom. So effective number of atoms per unit cell of a simple primitive unit cell is 1. Though we have 8 spheres to construct a simple or primitive unit cell, but effectively only 1 sphere is present per unit cell. Look at this body center. Okay. We have atoms occupying 8 corners, so we have 8 by 8. Number of face center is 0. Number of end A center is 0, but we also have one body center. So this comes out to be 2. So to develop a body center unison, we require 9 spheres, 8 corners and 1 body center, but effectively there is only 2 spheres per unit cell. In case of FCC, we have 8 corner atoms, so 8 by 8. Along with this, all 6 faces also have face center atom, and each face is equally shared by 2 unison, so that is 6 by 2. So this comes out to be 4. So to construct an FCC unicell, we require how many spheres? 8 corner atoms plus 6. So 8 plus 6, 14 atoms or sphere is required, but effectively there is only 4 atoms per unit cell. Now in case of this N center, we have J, we have 8 corner atoms plus we have 2 face, and each face is having face center. So number of face center atom is 2 and contribution is half. So this comes out to be 1 plus 1, 2. So BCC 2, ECC, sorry, 1 plus 1, 2. Primitive 1, FCC 4. This is what we call as effective number of atoms per unit cell, or simply we say ring. So once we identify the lattice point, we can easily define what is the effective number of atoms per unit cell. But to define this, we have to take this formula, simplest formula, and basically the point to be remembered is each corner atom is equally shared by 8 unit cell. So the contribution is 1 8. Each face is equally shared by 2 unit cells, so contribution is half. Each is equally shared by 4 unit cells, so contribution is 1 4, and each unit cell has one body center, that is only 1. So this is the effective contribution. So once we know this effective number of atoms and the arrangement of points in different forms of lattice point, now we'll find the formula of unit cell or formula of a compound. So first let me take some example. Question says a compound is formed by elements X and Y such that X occupies, means we have a compound, this compound is formed by X and Y such that in a cubic form such that X occupies corners of cube and Y occupies face center. So we have a compound is formed by X and Y forming a cubic unit cell such that X occupies the corners of cube, Y occupies the centers of face. So first calculate rank, second total number of atoms in cube, third formula. Second part of the question says if all atoms are removed from a single axis passing through the center. If all atoms are removed from a single axis passing through the center, then find the value of Z, total atoms in the cube, and the formula. So we have a compound formed by two elements X and Y in a cubic unit cell, such that X occupies corner, Y occupies the face center. Then question is find the Z. So X occupies corners. So in a cube there are 8 corners. So we have 8 by 8. Y occupies the face center. So in a cube there are total 6 faces and the contribution of each face is half. So we have 6 by 2. So that is 4. So for this first phase, effective number of atoms per unit cell is 4. Total number of atoms in cube. So cube contains X and Y, X occupying corners. So number of X atoms is 8, that is corners. Number of Y atom is Y occupying face. So total there are 6 faces. So total is 14 atoms is present in this unit cell. And the formula. If you look at this, contribution of X, we have X, effective number of X. We have 8 by 8 because X occupies only the corners of cube. Effective number of Y atoms, that is occupying face center, there are 6 faces divided by 2, so we have 3. So effective number of X is 1, effective number of Y is 3, so therefore the formula is XY 3. This is effective number of X atoms, effective number of Y atoms. Now coming to the second, if all atoms are removed from a single axis passing through the center. So we have looked at this. We have this. This is X. So this is X. Along with this we have Y. This is Y. Then we have front face. Then we have the rear face. The question says if all atoms are removed from a single axis passing through the center. Let this be the axis. So we have. So you are removing this two face center atom. All atoms are removed from a single axis passing through the center of cube. So this is the center of cube. So we have this axis passing through the center. Means we are removing two face center atoms on opposite face. So just now look at this. Then effective. So number of corner atom is 8. Contribution is 8. Number of face atom is left is 6 minus 2, 4. So we have 4 face atoms because these are the removed. Contribution is half. So we have 1 plus 2, 3 atoms. Effectively there are 3 atoms per unit cell. Then total number of atoms. Total there are X is 8 corner atoms. Then out of 6 face, 2 is removed. So how many left? 4. So Y 4. Total is 12 atoms in unit cell. The formula. Number of corner atom is 8. So effective contribution of X is 8 by 8, that is 1. Effective contribution of Y. Number of face center atom is 6 minus 2, so we are left with 4. And each face has a contribution of half. So this is 2. So therefore, formula of the compound is X, Y, So this is the formula. So this is how we define the formula from the lattice position. To make it clear, let me take some more examples here. Now again, we have a compound. A compound is made up of X and Y in a cubic unit cell such that X occupies corner and if Y, that is two atoms, the two Y atoms at each body diagonal. So we have a compound in which, in cubic form, in which X occupies the corner and there are two Y atoms at each body diagonal. So first, calculate effective number of atoms, total atoms. Third, formula. B says if all atoms from one body diagonal is removed. So we have body diagonals. From one of the body diagonal, atoms are completely removed. Then find the total atoms and the formula. So we have a cubic unit cell. So we have a cubic unit cell. And this we have X and Y atoms. So X occupies corners. So we have X occupying corners of cube. So this is your X. Then we have two Y atoms at each body segment. Now let's see how many body diagonals is present in a cube. In a cube, look at this. This is one body diagonal. So in this body diagonal, we have two atoms. Second, look at this. This is also body diagonal. Again, we have two atoms. This is third body diagonal. We have two atoms. This is fourth body diagonal. So in a cube, how many body diagonals are there? Four body diagonals. And each body diagonal contains how many Y atoms? Two atoms. This is one body diagonal, and along this one body diagonal we have two Y. This is Y. So total there are four body diagonal in a cube. Every cube contains four body diagonal. So coming to the question, okay. So we have corner atoms X. So number of corner atoms is 8, contribution is 8. Now we have Y, number of body diagonal is 4 and each body diagonal contains how many Y atoms? 2 atoms. So going to 4 because this body diagonal is the exclusive property of single cube. So this will not be shared with another cube. So therefore this comes out to be 1 plus 8, that is 9. So effective number of atoms per unit cell is 9. Total atoms, so let's count the number of atoms. X is occupying corners and Y body diagonal. Each body diagonal contains 2. So 2 into 4, so it comes out to be 16. There are 16 atoms in this arrangement of X and Y. Now coming to formula, effective number of X atoms is 1. Effective number of Y atoms. So Y atoms per unit cell is 9. 2 into 4, that is 8. So the formula is X, Y, 8. So this is the formula. This is the total number of atoms. This is effective number of atoms per unit cell. Now coming to the second part, question says, if all atoms from any one body diagonal is completely removed. So we have total 4 body diagonal. So out of this 4 body diagonal, atoms along a single body diagonal is completely removed. So let's take out these 2 atoms are removed. So one body atoms along one body diagonal is completely removed. So how many body diagonals is left? 3. And each 3 body diagonal contains how many atoms? 2 atoms per body diagonal. So therefore Z as usual. So we have 4 body diagonal. Out of these 4 atoms along a one body diagonal is completely removed. So we are left with 3. So 2 into 3 body diagonal. 6 plus 1, yeah, 7. Effective number of atoms per unit cell is 7. Total number of atoms is X is 8, Y is 2 into 3, so it comes out to be 14. 14 atoms is present in the cube. Formula: effective contribution of X, that is corner 1, effective contribution of Y, that is, so therefore the formula is X, Y, 6. This is the formula. So I hope you are getting the point. So we have to identify the location and the unit cell. Let me take one more example. Again, we have a compound formed by elements X and Y. X occupying corners of cube and Y occupies face center such that one X is missing from the corner. So we have a compound formed by X and Y. X occupying corners such that one X is missing from any corner. Y occupies the face center A. What is the J? Total atoms. What is formula? B. If all atoms are completely removed from one face, if all atoms are completely removed from one face containing atoms at corners, is in the above, calculate the effective total atoms formula. So we have this X occupying corners such that one X is missing from any of the corners. So we have X missing here. These are corner atoms and one corner atom is missing. Question says one X is missing from the corner, so there is no atom at this particular corner. So we have this X. Y contains face center, occupies face center, so we have this Y. Then what is effective number of atoms? So we have X. How many X? 1, 2, 3, 4, 5, 6, 7. 7. 7 by 8. There is 7 corner atoms. Is one corner atom is missing. And each corner contribution is 1 8. So total effective number of atoms per unit cell for this X is 7 by 8. We have phase center. Y occupying phase center. There are 6 phase and each phase center is having contribution of half. So this is 7 by 8 plus 3. 31 by 8. That is effective number of atoms per unit cell. Now coming to total atoms, there are 7 corner atoms, 6 phase center atoms, total is 13. Formula. Contribution of X is 7 by 8. Contribution of Y 6 by 2. So therefore the formula is X 7 by 8, Y 3. Now multiply by 8. So this comes out to be X7, Y 24. To make it simple ratio. Now, second part of the question says if all atoms are completely removed from one phase containing atoms at corner. So this is the phase in which one atom is missing. This is the phase in which one atom is missing. This is the phase in which one atom is missing. So question says you can remove all atoms from any phase containing atoms at corner. So let this be the phase in which 4 corner atoms. We can take this real phase also. We can take this phase also. So we have a phase containing atoms. So atoms along this phase are completely removed. That means 4 corner atoms and 1 phase center atom is completely removed. Then the number of corner atoms that is 1, 2, 3. If all atoms are removed from one phase containing atoms. So this is the phase containing atoms at corner. So atoms are completely removed. So number of X is left is 3. Contribution of corner is 8. Number of Y atom left is 6 minus 1, 5. So 5 by 2. So we have this state. X is 3 by 8 also. Number of X atom is 3. Number of Y atom is 5. Total is 8. Contribution of X 3 by 8. Contribution of Y 5 by 2. So formula is X 3 by 8, Y 5 by 2. So to make it simple ratio, multiply this by 8. So we'll get the ratio. This is how we define the molecular formula from that lattice position. So bodies we know should know the lattice position and draw the structure.